Oh, did you guys record for the deadline?
The yellow and the blue packet, we will be working problems from these as homework assignments, but I'll be honest with you, and I tell you, like I've told you, I don't try to mislead you ever. We won't get to the homework tonight, so there won't be a homework assignment tonight. There will be a quiz next time for sure, because I've got to do something to get you motivated to memorize the things you're writing down today. So make sure you get what we talked about today written down. It's mostly just symbols and terms. There's not really a whole lot of understanding. It's just a lot of writing. This packet has, we won't do homework for this packet, but we will fill out a bunch of stuff as far as notes. Lots of graphs, that's why the packets are 10 pages each, because the graphs take up a lot of room. So this is just for notes, and I printed it for you because it's hard sometimes to take notes when you have to draw the graph. It's a lot easier if you have the graph already drawn. So that's for your notes. We'll just do kind of random things today. Start off with memorize this, please. I don't know if you've heard these words before or not. Sometimes we have what we call a sometimes we describe something in terms of it's a qualitative description. I don't know if you've heard that word before or not. The other way to describe things is in a quantitative way. So we'll write both of these down so we can kind of compare them. So the qualitative analysis and quantitative. Put up here and pull up. Qualitative and quantitative. Qualitative means you're only estimating really. You do typically care whether the value is positive, negative, or zero, but you don't really care too much beyond that, other than you'll often want to identify whether the value is large, medium, or small. And if you're just comparing values, you're not really computing any values. Okay? When we say a qualitative discussion, that's what we mean is not really the details, just the general idea. It's more conceptual. And then quantitative is, precise computation. You actually compute the values, you don't estimate them. Accurate, that sort of thing. Okay, so I'll use those words kind of throughout the year a little bit. Today it's very qualitative. We're just getting terms written down. Just memorizing terms for the quiz next time. We will do some computations, but they're really estimates. They're not precise. We will care whether something's positive, negative, or zero, but beyond that, we don't care too much other than to say this thing's bigger than this other thing, something like that. So not really quantitative today. That comes later. Okay. Next thing to fill out your notes with is this one is an example. Hold on a second. Turn that off. So here's a table of values. You don't need to write down this table. Just kind of look at the board for a second. They're talking about a swimmer, and they say that they swam a length of 50 meters, and they did it in 24 seconds. And as you would expect, if you look at the distance that the swimmer travels, from time 0 to time 4 seconds, the swimmer travels 5 meters. But then once the swimmer gets up to full speed, down here between 12 and 16 seconds, kind of the middle of the pool, the speed is up to, they travel 10 meters in those 4 seconds, so much faster. In fact, the fastest length is right here between 16 and 20, where the swimmer travels 11 meters in 4 seconds. So So the speed is increasing as the swimmer goes across the pool. Then the speed starts decreasing again. For the last 4 meters, drops down to 9 meters are covered in those 4 seconds. We've done this before in a lot of quizzes. We've calculated the average rate of change of position versus time. And to do that, we have to specify what time period we want to calculate that average rate of change. So just for right now, we'll say that's from, let's say, for t equal 16 seconds to t equal 20 seconds. So you don't need to write this down if you don't want to. This is review. We've done this in a lot of quizzes. So average rate of change of position versus time for this time period. Last time I gave out some extra tickets. I really like the idea of giving out points for just kind of certain responses during class. It doesn't really work to do it all the time. That gets a little bit, I don't know, annoying. What'd you say?
Crazy.
Crazy after you start seeing points over and over again. So keep listening for that, though. And I think last time the way I paid, I can't remember, every class was a little different. Last time I believe I came around, and if you had earned, say, 22 extra points, I paid you 2 extra tickets. Is that correct? And then if you'd earned like 28 extra points, I still just paid you 2 extra tickets. Okay, to be a little bit more fair, what I decided to do is, if you earned 28 last time, I've already paid you the 2 full tickets, but you can keep those 8 points and carry them over for future days. Does that make sense? So you should be able to look back in your notes and say, oh yeah, I have, X, like Dawson's got, like, how many extras do you have? So I paid you for some of them. Very good. So he's got 8 extra. He can start today with 8 points. Kenna as well. I do have to be. I'm going to slow down a little bit. I got a little scared. It was a little bit crazy. But yeah, keep track of them from day to day. And then at the end of the day, I'll walk up and say, did you get the focus point, the focus ticket? Did you get the general participation ticket for participating? And how many extra tickets did you earn for your extra points? So, does that make sense? Cool. That makes it a little better for me. I can be a little more flexible in how I ask questions and things. So, without, as Kate says, getting too crazy with saying points all the time. So, it's a little better balance. Hallie had the class last year. She recognized that I'm trying to do a little bit different than last year's.
Yeah.
Back to work. Good work. She's like a model of homework. Good work. Makes me happy every time she walks in and sits down and does her homework. Good job. Cool. Now I'm embarrassing you. Sorry about that. Go back to work. Okay. Here we go. So to compute this, somebody just raise your hand and tell me what to do to compute the average or change here.
So you do the change in your distance.
Very good. So let's write that down. So we have the change in the distance traveled. I'm going to use a new symbol here. I'm going to use S. The AP test does this all the time. They refer to S as being the position of the particle, the person, the car, the whatever. So we're finding that change in the swimmer's position. Perfect. So point for Blakely. Somebody just build from there, please. For him. Just kind of follow her logic there. Let's go, Dawson.
We find that between 2 interval points, distance we find, like, so between points, there are 2, we actually see 3 points, which are from an average.
Oh.
41.
So, no, we just go
Oh, we
between
do nothing.
16, yeah, you just look at the wrong one.
Okay.
So we're just going here, you're perfect.
So we forward, over,
You just have to
oh,
say
30, 11 over 4.
There we go. You're doing great. So 11 over 4. And if you work that as a decimal, that would be, let's see, 2.75 meters per second is the average rate of change of the swimmer's position during that time period. We have a question about what we mean by average rate of change, point for Dawson. Okay, so that's average rate of change. Okay, now it's time to make a big list of things. So we get a blank page here. Okay, so big long list of words. So we have talked about average rate of change. I abbreviated that as just average ROC. Come up with different formulas for computing average rate of change. This is the stuff you gotta make sure you have memorized for future quizzes and homework and tests, etc. of course. So Dawson came up with one formula already. He said that's the change in the output divided by the change in the input. Somebody can please just pick up another point and tell me what's another way of expressing a computation that would find the change in the output versus the change in the input. Let's go here, Secant.
Y2 minus Y1 over X2.
Perfect. We just take the two output values, subtract them, find the difference, and then take the two input values, find that difference. That's a key word there. This is referred to as a difference quotient. Memorize that. You'll see that word on the AP test sometimes. Quotient meaning we're dividing difference because we're subtracting. Another way to write this is you could say the change in F divided by the change in X, point for Secant, there, ready to go. Which means we can write it like this as well. We can say it's the value of F at some X coordinate, subtract the value of F at a different X coordinate, divided by the difference in those X coordinates. So all these things mean the same thing. We often refer to this as the rise over the run. Questions? So that's all review. That's nothing new. Just check my notes, make sure I'm not forgetting something. Okay. In the past, you've applied this type of computation to some different quantities. So let's write those down. Let's go down here. So here's some symbols to memorize. We will often in this class talk about the position of something. Like in the last example was the position of a swimmer. The AP test likes to use these symbols to represent the position of something. They use the symbol S of t, or sometimes just S. They use the symbol X of t, sometimes just X. Y of t, sometimes Y. And I've seen H of t used as well, H usually standing for height. So when I say position, you have to be prepared to use any of these symbols to represent the position of something. They like to use the symbol X if the particle is moving back and forth, because it's similar to the x-axis. They like to use the symbol Y if the particle is moving up and down, because it's similar to the y-axis. They like to use the symbol S just kind of generically for like a car on the road or something. Height is used often for objects that are going up and down. So, questions? So memorize those symbols. Once they have defined this, they can have you talk about this in a problem. You can talk about the average rate of change of position. The average rate of change of position is also known as the velocity. Or V of t, or, oops, sorry, that would be wrong, back up. The average velocity. I'll fix that in your notes, hold on. So average rate of change of position is the same thing as average velocity. Like that. just like we did up above, that means you take the position at some time, subtract from that the position at a different time, and divide by the change in those times. How do you find the average velocity, or the average rate of change of the position?
So average rate of change of position is the same.
Perfect, perfect.
It's not divided by the.
Oh, thank you. Yeah, that does look a little awkward. So average rate of change is the same, average rate of change of position is the same thing as average velocity. That's perfect. Similarly, you will be asked to compute the average rate of change of velocity. Versus time. This is really the average rate of change of position versus time. Versus time right here. And they give a name for the average rate of change of velocity versus time. They call that the average acceleration. Find that by comparing velocities at different times. Okay, now, again, in this class, if you write something down and you're kind of like, just feel like you're just copying without making sense of it, feel free to do exactly what Kenna did. Extra point for Kenna. Just raise your hand, speak up, clarify what it is we're actually writing down. Try not to just write things down blindly. So, questions? Perfect. Let me check. Monday throws me off a little bit. Okay. I'll check my notes. Perfect. Okay. One more thing we want to put here is that when you're talking about the average rate of change of a function, another way to think of it graphically is you're talking about the secant slope. So average rate of change is the same thing as secant slope. Same thing as the slope between 2 points. Lots of notes today. Average rate of change, secant slope, slope between 2 points. So none of that is new. This is, oh yeah, please, Karen.
So the average rate of change of velocity versus time, that's just like the bigger part of average rate of change of position versus time, and then that's just, I'm a little.
You're doing just fine. No, let me just say, back to you said that very well. So the difference between what you're thinking and what it really is you can compute the average rate at which anything changes. Okay? So one thing we could compute, like we did in the swimmer's case, the example we did at the beginning, is we computed the average rate at which the swimmer's position is changing. Let me show that picture again. So this just shows, different times, different positions, and basically you're just saying, okay, between time 16 seconds and time 20 seconds, the swimmer's position absolutely changed.
Oh, so we just found the velocity right there.
The average velocity.
Average
Velocity. Because we found it, key things here, Paris. We found the velocity between one time and another. So it's the average velocity of the swimmer during that time period, or the average rate at which the swimmer's position is changing. Does that make sense?
So,
Right.
average velocity versus time, what's that?
That's what we just did.
Oh, they're the same?
So we often will just say average velocity because we don't want to have to say average velocity versus time. Okay, back up. I said it wrong. Let me say it again. So velocity is the same thing as, sorry, average velocity is the same thing as the average rate of change of position versus time. Those mean the same thing. There's just two different ways of saying the same thing. Does that make sense in your notes?
So then average velocity versus time. That's average acceleration.
Perfect. Perfect.
But what's average velocity versus time?
You just said it the same way. So one more time. You're okay. You're doing great, but just stay with me. Okay. Position simply means where the person is.
Okay.
Okay, so it's not a rate of change, it's just where the person is located. If we calculate the average rate of change of position, think of it this way. And I don't know if this is how it happened, but it helps me remember. For years, people would just say, hey, I want to calculate the average rate of change of position. And then somebody came along and said, I'm tired of saying average rate of change of position. So they invented a name, velocity. So average rate of change of position is the same thing as average velocity.
Okay.
They're the same.
Okay.
Similarly, we could calculate the average rate of change of the velocity versus time. But somebody got tired of saying all of those words, so they invented another word, acceleration.
So this is like the bigger picture of the average velocity?
They're more just like examples of different things.
Oh
So
my gosh.
position is one thing. Just keep looking. You're doing great. Position is one thing. That's just where the person is.
Okay.
Average rate of change of position says on average, what's the rate at which that position changes? That's the same thing as average velocity. Okay? This is a different example. Average rate of change of velocity is saying on average, what's the rate at which the velocity changes?
So it's like the rate of what the rate of, oh my gosh.
Yes. This is not a rate, this is just where you are. This is the rate at which where you are is changing.
Okay.
This is the rate at which that rate changes.
Got it.
So, that helps?
Yeah.
Good job. 2 points, Paris. Well done. Other questions? That actually was a superb question. It really was. It's very good, just like making sense of each of the terms. So, anybody else? Okay. Now that we've talked about what we mean by average rate of change of position and average rate of change of velocity, etc., we throw in a new word. The new word is instantaneous rate of change. So throw up a new page here. So instantaneous rate of change. Following up on Paris's comment, if the idea of average rate of change simply means how fast, what's the rate at which something is changing from one time to another. Really conceptually, which is all we care about for today, instantaneous rate of change is the same thing, except it's how, what's the rate at which something is changing at an instant. If you think of the swimmer, we can calculate average rate of change, and we did, by just looking at where the swimmer is at different times, and then computing this ratio. That's average rate of change. Instantaneous rate of change, think of it more like you have a radar gun, and you actually are putting the radar gun on the swimmer. Like as they swim across the pool, you're clocking them. You're just looking at it and saying, oh, they're going this fast right now. Now there's, now they're going this fast. Now they're going this fast. That's instantaneous rate of change.
So it's basically instead of looking at the graph as it flows, you're looking at individual points.
Yeah, listen to Aaron, please listen to that. 3 points for that. That's perfect. Instead of looking at the graph and saying, I want to look from this point to this point and see how the graph is changing, you're saying, I want to know how the graph is changing at a point. So average is between 2 points. Instantaneous is at a point. Really, that's all you need to know so far. Any questions on that? Well said. So back to here. Okay, there are a lot of symbols though. Let's start writing them down. Instantaneous rate of change. Okay. The symbol F, so F of X represents a function. Okay? So f of x is just some function. If you start with f of x, you can say that f prime of x, let's, well, one other thing here, sorry, 1 second. So another way to look at it is, f of x also means the y-coordinate of the function x, function f, sorry, of the function f at any x value. Right, probably should say x coordinate. So we think of f as being a function. So one way to think of the symbol f of x is it's representing the y-coordinate of the function f at any x coordinate. Question. So new symbol. F prime of x. It's not the number 1, it's an apostrophe. And the way we say this is we say f prime, like this, prime. It's like Amazon Prime. So f prime of x represents the instantaneous rate of change. So f prime of x represents the instantaneous rate of change of f, of the function f, we'll just do f this time, at any x coordinate. So it's very much what Aaron was saying. You're looking at the graph of f, and you're identifying how fast the graph of f changes at any given point.
Wait, is that f still f of x?
Uh-huh.
Okay. Same thing.
Same thing.
Okay.
I kind of run it both ways so you get used to the fact that they'll use it both ways.
Okay.
Sometimes they'll write f of x, sometimes they'll write f. So, questions? All right, more symbols here. So f prime represents the instantaneous rate of change of f at any x coordinate. The instantaneous rate of change, lots of words today. The instantaneous rate of change of f is also known as the derivative of f. So the instant, oh please David.
Why are we doing the f prime thing? Starting a little confused, like
No
what's
worries.
the point of the f prime?
So where we're headed is, in this kind of this example we did a minute ago at the swimmer, we just reviewed the idea that given this type of information, we can calculate an average velocity for the swimmer. Calculus is the study of instantaneous rates of change. So the whole idea is that you've actually never had a class before where you learned how to figure out how fast, the velocity of something at an instant. That's where we're headed. So, everything you've done to this point has always been average, unless you've already had AP physics.
Oh, you don't want to do normal.
Yeah, if you've had calculus-based physics, they have talked about instantaneous rates of change. Otherwise, you really haven't. It's always been average.
Well, sorry, where's your hall pass?
Oh, it's right there on the pin. Thank you. No worries. Thanks, David. Cool.
Where?
Just on the tray, right there. Perfect. So keyword here, derivative. When we talk about instantaneous rate of change, we're also talking about derivative. Now, Okay, I think I've told you this before, and you've already experienced it a little bit with the pink homework. The AP test likes to ask questions in a lot of different ways. Like we talked before how on that pink homework there was the example of, it says things like, is f of a defined? And then in a different question it said, did f of a exist? And they mean the same thing. The same thing will happen here. In one problem they'll talk about instantaneous rate of change. In a different problem they'll talk about f prime. In a different problem they'll talk about the derivative. And they mean the same thing. So you just got to get it memorized. Another symbol. F prime of x can also be written as d of f divided by dx. Okay, the d really stands for difference. And when you're finding instantaneous, it's an infinitesimal difference. So the D stands for difference. This D stands for difference as well. Get an infinitesimal difference. This is an infinitesimal difference of f. This is an infinitesimal difference of x. So this whole thing is again a difference quotient. And that difference quotient is the derivative. You guys are doing a good job of asking questions that tie the words together better than I can sometimes write them on the board. So does anyone want me to say this again, how this all fits together? Want to talk about it yourself and just confirm that you're thinking properly?
An infinitesimal difference. Like why?
Gotcha.
Different.
So what I'm going to, no, really good. The difference, you're doing just fine. So the difference is when we find a let me write a page here. Hold on. When we talk about average rate of change, we compute a difference in the output value divided by a difference in the input value. When we find a page all over the place, sorry. When we find an instantaneous rate of change, we're still doing a difference. It's just that the two output values are infinitely close to each other. So you're still actually taking a y2 minus y1 divided by an x2 minus x1. But instead of the points being some finite or fixed difference apart, they're infinitely close to each other.
So we're going to have to do plus and minus.
That's why we learned that.
Okay.
Yeah, the idea of limits was to lead you to the point where you could use them to understand this. Okay. Does that help a little bit? Perfect. Anybody else? Again, huge thing. And look here, eyes on the board for this one. The little d doesn't mean derivative. The little d means difference. And it's not a multiplier. It's not d times f of x. It's the difference of f of x. Like you're literally subtracting. And this d means the difference in x. You're literally subtracting x value. It's awesome.
Those equations would just define the derivative.
Very good. This is the equation you use to calculate the derivative, to find the instantaneous rate of change. The reason it becomes challenging is because those values are so close together. But it's very much like Kenna said, it's that same idea of saying, really close numbers, how do we subtract them? Please, go.
What's the difference of f of x to 1?
Just f itself. So think here, when we did the swimmer example, we found the difference in the output. We said, here's one output of 41, here's a different output of 30, the difference is 11. when we're finding the instantaneous rate of change, we're actually doing the same thing, but the 2 points are really close.
So how would it look if you were to do it?
It's difficult to write down exactly what it looks like, but here's the general idea. So it's like saying, if I want to find out the instantaneous rate of change of the swimmer's position at, say, this exact time, well, I'm going to be comparing numbers that are like this. One value would be like 30.0001. The other value is like 29.9999, like that. You're comparing two values that are infinitesimally close to each other, and you're subtracting them. You're finding a difference. That's the general idea. Does that help a little? So back to here. So again, just re-emphasizing what I said to Suganda. This whole quotient, this divided by this, that's the derivative. Don't think of the d as meaning derivative. It doesn't. It means difference. It's the ratio, the difference quotient, that is the derivative. That can confuse people. Good? Hopefully.
It's like every difference quotient a derivative, or like?
Only if you're comparing two things that are infinitesimally close. Really, and every is probably too strong. There's probably some example that I'm not remembering. But in general, if you're finding how the output of any function changes compared to how the input of the function changes on an infinitesimal scale, like just zoomed in super close between two really, 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 really close points, you're finding a derivative. The difference quotient really is the derivative. When we have the difference quotient on the other one, Stephen, I'll pay in a minute. I owe you. Hey, sorry. I was Stephen as well. Gotta start paying for the person who said the wrong name. At least I noticed. Okay, this was a difference quotient as well, but it's a difference quotient of points that are separated by something. Does that make sense?
Yeah.
Okay. Back to here. Awesome questions, really. Anybody else? Perfect. Let's see, more symbols. Okay, so here's one. Write this down, please. So, for example, f prime of, say, 8. F prime of 8 means, or represents, so f prime of 8 represents the derivative, or it's called the tangent slope now, because it's not the slope between 2 points. It's really, as Aaron said, it's the slope at a single point. So f prime of 8 represents the derivative or tangent slope, or, as I said to Paris, the instantaneous rate of change. Derivative or tangent slope or the instantaneous rate of change of f at x equal 8. That's the meaning of that symbol. It's the rate at which f is changing at exactly 8, x equal 8. Questions? Perfect. Keep going. Another symbol that you have to memorize is that sometimes they write it this way. F prime of x can also be written as d of, I think I did this above, so we go f of x dx, or dy dx, since we use y to represent f sometimes. So that means you can write this. F prime of 8 is sometimes written as d of f of x over dx at x equal 8, or it can be written as dy dx at x equal 8, or I've seen it written like this, d of f of 8 over dx. So those all mean the same thing. questions? Perfect. Catch up there one second. Nice, you got that. Gotcha. So the way you read it is you say, so this means the derivative or the rate of the instantaneous rate of change of f at any value, at any x value. This means the same thing at specifically x equal 8. So the way I read it is I say the derivative of f at, the bar means at, x equal 8.
Why don't you just plug in 3?
Like this, you mean?
Yeah.
There's just both ways. You'll see it written both ways. This is actually not very common. This is the most common is this one, but you have to know all of them because they test you on it. Please start.
So we're treating this like a whole, like I was kind of wondering why earlier you would use 49.99999 and 30.001. Why would you just do 29.999?
Gotcha.
Is it like treating it like a whole?
You can actually do the computation both ways. So for today, don't just kind of think of it as, you can think of it as saying, well, I'm going to get a point on this side and a point on this side. I'm going to squeeze them so close that I can tell what the slope is in the middle.
Okay.
Or the other way to do it is to say, I'm going to take it kind of from both sides. So that part's not super important for our class. Just the general idea is good enough.
Okay.
So done
Why don't you put in the 8 on the bottom of the
in the denominator? Only because whoever invented the symbol just decided they wanted to write it this way. That's just what they did. Like, I can say why you would think that's what you want to write. They just decided not to. So.
Well, like even in the last one, it says DFJ, and then it just says
I understand. They just decided not to write it that way. So. It's not like they couldn't have. It would make logical sense just to write it the way you're describing it. Someone decided not to. Other questions? Perfect. Okay, when we were talking about the average rate of change, Paris had a really good question. She was clarifying the difference between position, average velocity, average rate of change of position, average rate of change of velocity, and also average acceleration. So we had all these different symbols for position. Because of that, you can now use those same symbols over here when you're talking about instantaneous rate of change. So down here, we can write that the instantaneous rate of change of position versus time, same thing again, that's exactly the same thing as the instantaneous velocity. And again, there's a list of symbols there. So you can say that's S prime of t, or you could say it's d of s of t over dt, or you could say it's ds over dt, or you could say it's x prime of t, or d of x of t over dt, or just dx over dt, or you could say it's y prime of t, because all of those symbols represent position. Or h prime of t, dh of t. Yeah. And finally, or you can just say it's v of t, or just v. You just have to be prepared to see all of them. So please go.
So if something has a constant rate of change, it's the same the entire time. Were there instantaneous rate of change and there just rate of change?
Yes, it's very good. Perfect. I'll give you 3 for that. It's a very good observation. No, really. She said that if anything has a constant rate of change, then the average rate of change and the instantaneous rate of change are the same. because the rate of change isn't ever changing. So at any given instant, the rate of change will be the same. It's very good. Perfect. Anybody else? Okay, so that's instantaneous rate of change of position versus time. Similarly, we can make a list of the instantaneous, this one's a shorter list, thankfully, instantaneous rate of change of velocity versus time. And we call that the instantaneous acceleration. And symbol for that would be v prime of t, or you could say d v of t over dt, or dv dt, or you could just call it acceleration. Yes, sorry, it's a long list today. I do apologize for that. I had you write it because you actually do memorize it better if you're writing it as we talk about it. So if you kind of hand out a big list, it doesn't really work as well. So. Questions? Perfect. Okay, here's what we mean by, let's caught up on that, sorry. One last thing to do today before we pay tickets. If you turn to this sheet right here, so in the white packet, go to this page here. It's like about 3 pages in. I'll put it up on the main board. It's in the white packet about 3 pages in.
Did you write it down?
Actually, go 1 page before that. So this one here. Just 1 page before that. There we go. So everyone can get tickets for these next few questions. So this is f of x. Hold on. So this is f of x. So just reviewing quickly, everyone who knows, raise your hand. I'll pay everyone who raises their hand and who is correct. So just look at f of 2, sorry, negative 2. Look at f of negative 2, and you don't have to have a perfect answer. We're just estimating today. So raise your hand when you can tell me what's the approximate value for f of 2. Just look at your graph. F of negative, keep saying it wrong, really sorry. F of negative 2. And they like, wait a second, which one do you want? F of negative 2. Hands up, you know, everyone who raises their hand and who's correct. So f of negative 2. So Rachel? Rachel says negative 16. I think that's a good estimate based on the graph. Question. Somebody got that one? Show me your hands if you got it. Just make sure you got it. So we're going to put down 2 for that. That's how you find the y coordinate, okay? If we're finding this, look, different thing. F prime of negative 2, I'm no longer looking at the y coordinate of f. I'm looking at the rate at which f changes, which means the slope of f, which means the tangent slope of f. Come over here to the point, and I think of a tangent line. Tangent line would look something like this. That's not really that great of a tangent, but it's decent, okay? And we don't care about being perfect at this point, just the general idea. The slope of this line, think of it as though you drew it between 2 points, as I said to Suganda, 2 points that are really, really close. that's what you're doing. You're drawing the slope between 2 points that are really close. The slope of that line is the value of f prime, because f prime represents the slope of the line tangent.
How do you know which way the line is going? Do you just follow the function?
Just follows the function. So here's a few more. If I come to this point here, the tangent line will look something like this, roughly. I go to this point here, tangent line looks like that. Does that make sense? You can estimate, watch me, you can estimate the slope of the blue line by just counting. Again, we're not trying to get a perfect value, just kind of an estimate. So if I find a place where I can count kind of easily, like, I don't know, that's, looks like it goes over about, let's see, that's not quite 1, but close. So 1, 2, 3, it's kind of going over about 3 boxes while it goes up. 1, 2, 3, 4, 5, it's kind of over 3 up 6 roughly. So 3 boxes over is 1.5. So I'm trying to find this slope. It's going to equal, let's come over here. So this is going to be about, we went over 1.5. We went up 6. 6 would get us to 15. Let's see, did I do that right?
So if you look at 3 boxes,
I think I'm doing something wrong.
and they're all 0.25 is 1.5, so it would be in between.
So 3 full boxes is exactly 1.5 over, right? Oh no, it's 0.75 over.
Yeah.
That's my mistake. Thank you. You can tell something's wrong there. 0.75. Somebody on your calculator real quick, what's that equal?
I thought it would be 0.125.
So this is 0.25, this is 0.5, so this is 0.75, 3 boxes.
Yeah.
So what's 15 divided by 0.75? 20. Our estimate's not too bad. This comes out to be 20. On a subsequent page, they calculate it to be 24. So they used a computer to calculate it versus just kind of counting. So we're pretty decent. But that's the idea of half. Again, no homework tonight. We're out of time. Remember, I'll pay your ticket to start of class next time if you remind me. So, it'll work. Oh, so all it was not.
Just trying to like make it look.
Whatever point. It doesn't matter. So I can start here and just go just like a point. And go 1, 2, 3, 4, 5 over. Not quite 5. Let's see. So 1, 2, 3, 4 boxes of 1.
Well, enough people like.